Hello everybody and welcome to the NPTEL online certification course on microelectronics devices to circuits. In our previous interactions we have actually looked into BJT as an inverter and we have understood how BJT's inverter can be made using a simple common emitter emitter grounded BJT. We also seen that the noise margins are not equal. So, basically NML and NMH are not equal, right, and therefore, though therefore a BJT will be a good acceptor of 1, it might not be very good acceptor of 0 or receptor of 0, right. So, if your low noise margins are typically very low, then even a small noise when you are inserting 0 will result in a change in the value of your output voltage. And that is the problem area of a BJT, that your noise margins are relatively not very high and therefore, you generally get a noisy reception in the output side. So first thing. The second thing is that typically, as I discussed with you, since you have to if you want to use it as a switch, you have to move from saturation to cutoff and vice versa, and therefore removal of charge carriers from saturation will take some finite amount of time, right, and therefore the time taken to switch from cutoff to saturation and back to cutoff, there is a finite time, and therefore you will always have a limitation at which the BJT can work in terms of frequency limitations. What we will be now looking is basically into bipolar technologies second order effects, which means that the first order effects were primarily the drift diffusion phenomena which the bipolar technology works, and we have also seen the current equation there. We will be now looking at some second order effects, which means that those effects which generally do not rise as such, but may become prevalent under certain conditions, right. So, under certain conditions they might show their influence on the current voltage characteristics of the device, otherwise they are quite silent and they do not they are not so much receptive to variations. So, what we will be looking therefore is one is the drift in the base region, and what people have done, and I will just like to show you what we have done here is that if you look at this equation INX which is this one, right, this one, the first part, so this is the total current because of the charge carriers which is there in the region. So, I have got PN transistor, right, and within that, as I discussed with you, the P region. So, I have got N, P, N. N has got the largest doping, highest area, P has got the minimum doping and minimum area, and N has got the or collector has got the relatively moderate doping. So, what I am trying to tell you is that from this point, let us suppose this accounts to x equals to 0 to this point which accounts x equals to say xn, then we know that the how is the electron profile, which is basically the majority current carrier in the p type base varies, right. So, this is what I wanted to discuss with you in this case. So, if you go back to this slide, you can see that so if you look at this figure 3 which you see, this is basically known as a graded doping, and you can see here that what we try to do is that we first make an acceptor grading. So, acceptor background is there. So, this background is basically acceptor, which means that all of it is basically made as p type first of all, right. We make it all p type, right, the whole of it we make it as p type, and then what we do is that we then dope it with with donor atoms. So, this is the donor atom which we are doping with, and then we ensure that the donor atoms exceed the acceptor atom at certain regions, which is between this point and this point, and therefore these 2 points are basically the edge of the base. So, this is my base for a p plus N P BJT, since your ND is larger than NA at this point and at this point, right. So, they are larger in the sense that they are more in value. So, I would expect to see a larger donor concentration, and therefore this will become more N type as compared to P, and that is the reason you get P type here. In this region, of course, NA is therefore larger than ND, and therefore this is basically your p type. Since it is very large, as you can see it is quite large as compared to Nd, we refer to this as a p plus region because the doping is very high, right. Similarly, when you reach to this side, your acceptor your dopant Nd, the donor ion actually reduces much below the value of your acceptor ion concentration, and as a result this becomes a p type. So I have got a p plus Np. So how do you do it? This is also known as a graded junction doping or a graded doping profile, and what we do here is, therefore in a graded doping profile we can control the width of my base as well as of the emitter as well as the collector by simply changing the dopant profile, right. So doping profile, right, that is very simple and easy to do action. You can also change the doping. For example, if you wanted to make this one more p plus type, so you want to make it p plus plus, then you simply increase the acceptor ion concentration in this manner. You wanted to shift this line from this side to this side, then you need to cut somewhere here. So when you cut the Na here, the starting value comes out here. So I can do all sorts of manipulation, and I am able to achieve a very straightforward methodology of having p plus n. Now let us suppose your electrons are the majority current holes are the majority current carriers, therefore electrons which are there are basically your minority current carriers. What we are assuming is that let us suppose the effective charge carrier at a particular place is nothing but Nd minus Na, right. So you had Nd, let us suppose 10 to the power 15, and Nd was 10 to the power 19 and Na was 10 to the power 15 or 16, then you subtract both of them and that is the effective Na or the effective number of dopant species. So if we have 100% ionization, I would expect to see that many number of free charge carriers. If Nd is greater than Na, free charge carriers electrons, if Na is greater than Nd, free charge carriers as whole will be of course available to you. Now to understand this, let us suppose I have electrons as the majority current carriers, then I define the current In at any point xn within the circuitry within the BJT. So this is the value, so this is the x variation, this is the x variation is equals to q times a q a mu n into n xn into E xn. I will explain to you what these terms are. N is the charge density or the dopant charge density which you see, E is the electric field from base to the emitter to the base region, E electric field at that particular point, Q is the electronic charge, A is the area of the cross section of the emitter or the base, and mu n is basically the mobility of the charge carriers, right. So this is basically by virtue of your sort of a drift current which you see, right. Similarly, you will also add a current which is by virtue of diffusion, because please understand that the doping within the base region is not fixed, right, it varies, because as you can see here Nd is varying like this. So I would expect to see that at 0 width, at 0 when the base starts, the doping concentration is maximum and then it starts to fall down in this fashion, right, and that is what is shown here, that I have got maximum width here, maximum number of doping concentration, and then it starts to fall down as we move from the edge of the base to the edge of the emitter to the edge of the collector. And therefore we have a diffusion term which is given as q a dn dnx dxn, which means that it is the charge, again A is the area, right, D is the diffusion constant for electron or a diffusion coefficient for electron, and dnx dxn is basically meaning the number, how the number of charge carriers are varying within this point. Now please understand, if the doping concentration within the base side would have been constant, this term would have been equals to 0. Constant means independent of the distance, the doping is always fixed. So if it is 0, the only contribution would have been only from the drift component and not from the diffusion component. And all of you can therefore understand that, therefore obviously the drift component will have always a component which is primarily proportional to the area as well as to the effective number of charge carriers or number of charge doping species in that particular point. Similarly, from Einstein's equation or from otherwise, we can find out that E of xn means electric field at any particular point xn is given by this formula, the same formula which we get, right, and we can, from there we can get the value. So it is very simple and straightforward. From this equation only I can get this very easily, right, provided you make the drift current equals to 0, then I get dn by mu n into 1 by nx dx and dy is equal to minus kt by q, right, 1 by nx and dnx, and because why it is kt by q, because d by mu n is equals to kt by q. Kt by q is constant at 300 Kelvin, approximately 26 millivolt to 25 millivolt. So, d by mu n is always a constant quantity, right, at 300 Kelvin it is a constant quantity, and therefore, we can safely write down this d by mu n to be a constant, and that is equal to minus kt by q, equals to minus kt by q upon 1 by nx and dnx and dx. Therefore, the total electric field at any particular point Exn will be a strong function of how the diffusion species is varying with respect to space, right, that is very important, which you see here. It will also depend upon the number of dopant species available at a particular point Xn within the network. If that is very large, the electric field, the absolute value of electric field will be fall, right, will be falling down. So, we have understood therefore, that in the base region, if there is a small amount of change in the value of Nd, I will have the drift in the base region. Therefore, there will be a drift carrier, there will be a drift, electron will be drifted through the base region, right, and that is quite an interesting phenomena which people see. So, as you can see, there is a fairly sharp discontinuity in the doping profile, right, your doping profile shows a sharp discontinuity, which means that since the doping, and the reason being that there is a sudden change at the interface between Nd and Na, right, and therefore, there is a sharp change. So, as you can see, the donor concentration in the base region becomes smaller than the constant p type background doping in the collector, that we have already discussed in our previous slide. We have already discussed that the donor concentration in the base region, right. So, if you remember the previous discussion was, sorry, the previous discussion, if you look, this is p plus np, right, this is p plus n and p. So, what I am trying to tell you that the donor concentration in the base region becomes smaller as compared to the collector concentration on the collector side. So, on the collector side you still have p, but on the base side, since donor is slightly higher, you get n region available to you, and as you can see, emitter is heavily doped shallow region, it is a heavily doped region. Why? Because the acceptor concentration is much larger as compared to the donor concentration there. Now, the net doping concentration Nd minus Na varies along a profile which decreases from emitter edge to the collector edge. This we again discussed. The why, and the reason being very simple, that if you look very carefully, the Nd is falling from this edge to this edge, right, and since it is Nd minus Na, right. So, since Na is constant at this stage, I would expect that the profiling here will also between this point and this point, right, parallel to this line, right, fine, and that is what you get, that it is varying, it is maximum at the emitter edge and minimum at the collector edge, right. Doping distribution in the base is basically can be simulated using Gaussian. Gaussian functions or Gaussian doping concentrations, something looks like this. It is not an inverted dumbbell shape doping profile. The idea here is this is known as, so if this is maximum, right, and this is say this is x, then this is approximately x by 2, and we define this width, right, we define this width as full width at half maxima, right. So, we define full width at half maxima, FWHM, right. Now, if you make it FW, so this is basically the distance and this is the doping concentration. So, this is Nd and this is the x, right. So, this is minus x plus x 0. So, 0 you have the highest doping, and as you move from highest doping to left and right, it falls down. Now, if you want to make the doping very sharp, you just have to make your FWHM very small, right, you have to make it FW. If you want to make the doping very constant doping, to something like this, spread out, right, spread out, and then your FWHM becomes large. So, what is the advantage of a Gaussian profile? The advantage of a Gaussian profile is that it helps you to give a profile or it helps you to control the profile from maybe a constant profile, constant doping profile to a sharp peak profile, by simply changing the value of your FWHM or full width at half maximum, also referred to as sigma in most of the cases, right, sigma in most of the cases, and that is what you refer to as a standard deviation, but technically it is full width at half maxima, and therefore you can see that automatically what you get from here is that simply by changing the value of FWHM, either you can reach a peak value of doping concentration or you can actually reduce the doping concentration drastically, right, and so on and so forth. So, this is what we get. The area under this curve is basically the total number of dopant species, total number of dopant species, dopant or acceptor, whatever you want to do, right. So, that is the reason Gaussian profile is most preferred profile in a design, because you can control it in a much better manner. So, due to a graded base region, a built-in electric field exists from emitter to collector, thereby adding a drift component to the transport of holes across the base. This is very important, right. So, you see what I was talking about in the previous case, that what is happening is, if you just look at it, that because of the graded base region, there is an electric field from emitter to collector, right, for a PNP, right, and therefore, so if there is a electric field, for example, from this direction to this direction, so if you have holes entering the base region, that will be always drifted by the strong electric field towards the collector side, right, and that is the reason it drift in the base region, right. So, that is the reason what we get. So, advantage of it is that you get a larger number of charge carriers on the collector side because of this drift in the base region, right. We come to the next second order effect, and that is basically known as early effect, or what is also known as base width modulation effect. We have already studied this, but I will just go it a bit fast in this case, so that you understand the issues in a much more detailed manner. Base width narrowing effect or early effect is to do with what, that if you remember, your base is lightly doped, as I have written here, this is lightly doped, and your what happens is that if your base is lightly doped, so I have got emitter base and this is emitter base and collector. So, emitter base junction will have a depletion region like this, and collector base will have something like this. But as I have told you previously also, that the depletion thickness will be larger towards that region whose doping concentration is low, right. So, what I am trying to tell you therefore is that if I have a PN junction or maybe an NPN transistor, which is a BJT, and let us suppose this is emitter base collector, and since base is relatively lowly doped, I would expect to see the doping concentration something like this. So, you will have like this, they are not equal. Similarly, this will have like this and you will have like this, but since emitter base junction will be forward biased, so this total distance will be smaller than this total distance, clear. So, what is the effective base width now is this much, this is the effective base width where doping is there, otherwise these are all fixed charge carriers, these are all fixed charge. This is the only place where you have a mobile charge and those are holes, and these are fixed charge here. So, basically they do not contribute to the overall current. Now, as I discussed with you, when you are active forward mode, your base collector is always reversed biased, right. So, when you reverse bias it, that means if this is NPN, let us suppose, if you reverse bias it, then this will be something like this, right. So, once you reverse bias it, this depletion thickness will further increase, as we had discussed earlier, that means reverse bias will increase the depletion thickness. So, the effective depletion thickness increases this side. So, what happens to the effective base width? What happens to your effective base width? It reduces actually, if you see very clearly. So, your effective base width now becomes this much, fine, it has reduced. When it is reduced, so this is basically known as therefore base width reduction or effective base width reduction. So, once it reduces, now you have lesser number of carriers in the base region, and therefore the electrons moving from emitter to the base side, the recombination will be smaller and larger number of electrons will be reaching to the collector side, and you will be reaching a very large value of alpha very close to 1, which is 0.99 maybe, right. And if your this base region would have been quite thick, your recombination would have been higher and the collector current would have been much smaller as compared to your emitter current. So, with this fundamental understanding, we just now come to the, so the depletion thickness at the reverse collector junction can be extended significantly into the n type base region. We have discussed this point, and the decrease in the base width causes beta to increase and alpha to increase as well. Hence, the collector current increases with collector voltage, right. So, what do we please understand, till now we were assuming that the collector current is always constant independent of the value of VCB, but now what we are seeing is, since now beyond a particular higher value of VCB your effective base width is reducing, I would expect to see an increase in the current. So, that is what we are seeing also. So, as you can see here, the current is increasing, it is saturating. So, if there would not have been an early effect, it would not have been something like this, right, it would have been something like this constant. But then what is happening at a higher value of VCB, VCE or VCB, your this profiling is becoming high, right, which means that what is happening is that this value is becoming high and therefore IC becomes large. Now, the way how to find out the voltage at which this happen is that if you back it, all of you extrapolated or interpolated backwards all the line, the place at where it meets is defined as by early voltage, right, this is known as early voltage, right, and early voltage therefore is that voltage at which they will start behaving like a fixed current source, right, and this is what the value of current is. Let me come to the third second order effect, and that is the avalanche breakdown, and I think it is very simple and straightforward. Avalanche breakdown is, remember your base collector is always reversed biased, right, we had been talking about for this long time that base collector will be always reversed biased. So, when the base collector is reversed bias, so you will have minority current carriers holes here and you will have electrons as the minority current carriers here, right. Now, when you reverse bias it, electrons from n type and holes from p type will not be able to move because the depletion thickness is very large, but for the minority current carriers which is hole on the n side and electrons on the p side, it is more of a hill, it is going down, it is not an uphill, it is a downhill, right. So, therefore, I will expect to see a large amount of current because of minority current carrier, but since the number of charge carrier minority current carriers are very low, therefore, the charge associated with it or the current associated will be very small. Yes, it will be small of course, but let us see what happens. Now, this once they start moving, so I have this junction, this is emitter base junction, and I have got NPN and electrons are available here and holes are available here, right. So, the electric field internally which is there in the depletion region between P and N, because it is reverse bias, so I have a depletion region here, right, and I would expect, so the internal electric field will be from this side to this side. So, any hole any electron trying to enter from this side to this side, electron is a majority current carrier in n type, will be forced to go this side. Similarly, any hole entering from this side to this side will be again forced to go this side. So, any majority current carrier contribution will be almost 0, anything which will be coming will be directly coming from emitter. But for these holes and electrons which are minority current carriers in collector and base respectively, if the hole enters here, it will be dragged by this electric field within the depletion region to reach this point. So, if you go on increasing the value of your reverse bias collector junction, right, if you go on increasing it drastically, so these electrons and holes will gain large amount of energy, and when they pass through this depletion region, they will ionize and form electron and hole pairs. So, what will happen is, beyond a particular point you might have a suddenly large increase in the value of electron, right, and that is what is known as an avalanche breakdown, that due to this sudden electron charge you will have a large electron current, and therefore, if you plot IC versus VCB, it is this constant, we have discussed this point, constant current, but as you go on making it more and more negative biased and make it larger, suddenly a time comes when the current suddenly increases almost drastically like this, and the reason is that you now have large amount of ionization and large amount of electron hole pair formation, because of which there is a large current available to you, right. These are primarily electron hole pair formation which take place. You can also have another thing, that electrons move very fast and they ionize the atom. So, the exterior most electron from the kinetic is the kinetic energy of the incident electron is so large that it directs its all energy to this peripheral atom electron, and the electron comes out of the atom, right, and it becomes a free electron. In any case, you will have a very large quantity of free electrons which will be available, and therefore you could expect to see a sudden increase in the current. This breakdown voltage is defined as VCBO when it is a common base configuration, also referred as BCEO, BV suffix CEO when it is a common emitter configuration which is there, right. So, we have these two types of configurations available. This is the net current which one sees because of the multiplication factor, because of m is the multiplication factor, primarily meanings that for each ionization how many number of electrons are formed. So, if one electron comes and form 4 electrons, then the multiplication factor m is equals to 4, right, and you will have 4 number times of electrons and hole currents available, right. So, with this we have understood the basic three mechanisms of breakdown. When we meet next time, we will be actually looking into the next two mechanisms in second order effects. As you can see, therefore, these are special cases as I discussed with you. Why special? Because only when a collector base or base collector junction becomes larger than this breakdown voltage, then only you will expect to see a very large increase in the current. Otherwise, the current will be almost constant or remain as it is. So, therefore, these effects are known as second order effects. What we have learned, avalanche breakdown, we have learned one. We have also learned your drift of charge carriers within the base region, a second order effect, and we have also learned about the early effect or effective base width modulation. When we meet next time, we will be actually looking into the other facts as far as this dimension goes, and we will see what are the other facts. We will look in thermal effects, and we will be looking into the base resistor or emitter crowding effect. So, these two effects we will look, and that will ensure that we will be finishing off BJT with the understanding of these few fundamental things. Thank you very much.